Hello, my name is Athena Lee, and my presentation is on active noise control or active noise cancellation. When we think of noise control, earplugs and phone probably come to mind, and these are the traditional ways of noise control, generally referred to as passive noise control. But ever since the early 20th century, the basic idea that destructive sound waves or anti-noise, which are 180 radians out of phase with the incoming sound, could cancel out these noise has existed. This would be the start of active noise control. In 1936, Paul Legge published a patent which would be the first to describe the basic ideas of active noise control and proposed a feed-forward structure within it. Then, in 1953, Harry Olson and Everett May published a paper in active noise control which emphasized no prior knowledge of the sound field, which makes their structure a feedback structure. The difference of the two we will discuss later. And after 1950s, a period of quiet existed due to the lack of better technology in this area. And this would last until the 1990s when papers and research started focusing on this area or active noise control once again. There are numerous applications in active noise control which have been shown to be most successful in situations where low frequency noise is the dominant problem. So we first have active noise control headsets, which can reduce an additional 10 to 15 decibel compared to the usual headsets for up to 500 hertz. Then there are the feed-forward headsets designed specifically for noise reduction in nuclear MRI that require headset without metal. Finally, we have active noise control for car engine firing sounds, especially at higher speed, and especially for modern cars, which tend to be lighter and have smaller and more powerful engines. So how does it all work? I've mentioned the basic principles of ANC before, but now I will specifically talk about feedback and feed-forward ANC systems, which use the LMS and FXLMS algorithm for adapting the destructive sound waves to the sound that the system seeks to cancel. So here, feed-forward ANC is useful when the reference signal is available and more effective against broadband noise. Uh, uh, we have a diagram here of a feed-forward ANC, and it works as follows. So the reference signal XN, note reference signal isn't necessarily the sound signal itself, is sent out by the noise source and travels along the primary path PZ before reaching the cross circle, which is the error microphone. The reference signal also travels through a secondary path and to HZ, which is an adaptive filter which uses the reference signal to produce the anti-noise YN, which travels along SZ path to reach the error microphone along with the original reference signal mentioned before. So the anti-noise and noise signal reach the error microphone, while the anti-noise creates a zone of quiet around the error microphone. An error signal, then EN, is produced. So EN travels to the LMS algorithm, which can detect the error in phase difference between the noise and anti-noise signal. According to a series of calculations, it will adjust HZ or the adaptive filter accordingly so that the anti-noise produced can be as out of phase with the reference signal as possible. And now on this slide, we have a feedback ANC, and it is useful when the reference signal isn't readily available, and so generates its own reference signal with the adaptive filter, and it is shown to be more effective against narrowband noise. And from the diagram, we can see a feedback ANC, and it works as follows. So here, XN is still the reference signal, YN and YSN is still the anti-noise, EN is the error signal, and HZ is the adaptive filter. And we can see that there are two error microphones, which are circles with a cross inside. Now, the top microphone receives the anti-noise signal and a direct sound signal, so YSN and DN respectively, producing an error signal EN. This error signal travels down and meets with the Y cap SN, which is the anti-noise signal, coming together to form the reference signal XN, which travels to HZ, the adaptive filter, and it takes the XN to generate anti-noise. It is also the signal along with EN, which travels to the LMS algorithm that adjusts the HZ accordingly. And then there are also hybrid ANCs which combine the two and other less common ANCs, but I do not have the time to talk about that here. For further studies, there are still three major areas that are in need of development. First is theory of associated acoustics related to ANC algorithms and positioning of microphones, speakers, etc. for optimum performance. Second will be development of adapting algorithm, which is more robust and can converge faster to the incoming sound signal. And thirdly is the practical implementation of the system in terms of its complexity and cost reduction. And there are also further application possibilities for ANC, such as putting it in motorcycle helmet, infant incubator, and also there has been has been news of snore ANC systems as well.